When we say the universe is 13.8 billion years old, we rarely pause to consider what happened during its very first heartbeat, that opening second when everything began. The number feels abstract, too large to hold in the mind, so we move past it toward things we can more easily picture: stars, galaxies, the Earth itself. Yet that first second contained more distinct physical events, more transformations, more changes in the fundamental nature of reality than all the billions of years that followed combined. Tonight we travel through every era of cosmic history, beginning with a single second that held more than any other second ever would. The universe, at 1/1,000,000,000 of a trillionth of a trillionth of a second old, was nothing we could recognize, nothing that resembles the cosmos we see when we look up at the night sky. The temperatures exceeded anything that exists today by factors so enormous that the numbers lose meaning when we try to speak them aloud or write them down. The forces we know, gravity, electromagnetism, the nuclear forces, had not yet separated into their distinct identities, but existed merged together in ways physics can barely describe. This was the Planck epoch, named after the physicist Max Planck, a time so brief and so extreme that our equations grow uncertain when we try to calculate what actually occurred. You are listening to the Drowsy Astronaut, and tonight we journey through every second of 13.8 billion years, from that unimaginable first moment to the present where you rest now, listening. This is not a quick survey, but a slow exploration, giving each era the time it deserves, allowing the story of the cosmos to unfold at a pace that welcomes sleep whenever it arrives. By 1/10,000,000th of a trillionth of a trillionth of a trillionth of a second, the first of the four fundamental forces had begun to separate from the others, gravity becoming distinct while the other three remained unified. This separation, called symmetry breaking, released enormous amounts of energy that would drive what came next in the infant universe's development and expansion. The temperatures had dropped from their initial extremes, but remained beyond anything we can experience or truly comprehend. Hotter than any star that would ever exist. The universe at this moment was smaller than an atom, yet contained all the energy that would eventually become every galaxy, every star, every planet, every living thing. What happened next remains one of the most remarkable events in cosmic history, a period called inflation that lasted from about 10 to the minus 36 seconds to 10 to the minus 32 seconds after the beginning. During this inconceivably brief window, the universe expanded faster than light, doubling in size again and again in rapid succession, growing from smaller than a proton to larger than a grapefruit. This expansion was not movement through space, but the stretching of space itself, which is why it could exceed the speed of light without violating any physical laws. By the time inflation ended, the tiny quantum fluctuations present at its start had been stretched to cosmic scales, seeding the patterns that would eventually become galaxies and clusters. The inflationary period smoothed the universe in ways that explain observations we make today, flattening any curvature and evening out the distribution of energy and matter. Without inflation, the universe would be lumpy and curved in ways that do not match what our telescopes reveal when they look at the large-scale structure of space. The theory of inflation was proposed in the early 1980s by physicist Alan Guth and has been refined by many others since those initial papers appeared. It remains one of the most successful explanations for why the universe looks the way it does, even though direct evidence for inflation continues to be sought through observations of ancient light. After inflation ended, the universe entered what physicists call the electroweak epoch, when electromagnetism and the weak nuclear force were still merged together as a single interaction. The temperatures had dropped enough for the strong nuclear force to separate and become distinct, but further cooling was needed before the electromagnetic and weak forces would go their own ways. During this era, particles and their antiparticles were constantly being created and destroyed, popping in and out of existence as energy converted to matter and back again. The universe was a seething soup of particles and radiation, everything interacting with everything else in a continuous, chaotic dance. Around 1/1,000,000,000 of a second after the Big Bang, the temperature dropped low enough for the electromagnetic force to separate from the weak force, giving us the 4 distinct forces we recognize today. This moment also gave mass to certain particles through a process involving the Higgs field, which had been waiting for the universe to cool sufficiently to condense and interact with matter. Before this transition, particles like quarks and electrons were massless, traveling at the speed of light, unable to form the stable matter that would eventually make up atoms and stars. The Higgs field filled all of space, and particles moving through it acquired mass depending on how strongly they interacted with this cosmic molasses. The universe, at 1/1,000,000th of a second, was filled with quarks and gluons moving freely in what physicists call a quark-gluon plasma, too hot and energetic for quarks to bind together into the protons and neutrons we know. This plasma was the densest and hottest state of matter that has existed since the Big Bang, conditions that scientists have briefly recreated in particle accelerators to study their properties. As the universe continued expanding and cooling, the energy available dropped below what was needed to break apart quark combinations, and quarks began binding together permanently. By 1 microsecond after the Big Bang, protons and neutrons were forming, the building blocks that would eventually make up atomic nuclei. The transition from free quarks to bound protons and neutrons marked a fundamental change in the nature of matter, a phase transition similar to water freezing into ice, but far more consequential. Before this transition, the universe was a plasma of fundamental particles. After it, composite particles existed that could eventually form atoms and molecules. The strong nuclear force, now distinct and operating at full strength, held these new particles together against any attempts to break them apart. The universe at this moment was still unimaginably hot and dense, but the pieces needed for chemistry and eventually life were now in existence. By 1 second after the Big Bang, the universe had cooled to about 10 billion degrees, still fantastically hot by any standard we can relate to, but cool enough for important new processes to begin. Protons, neutrons, electrons, and photons filled space in a dense plasma, constantly interacting, but beginning to settle into behaviors we can calculate with confidence. The ratio of protons to neutrons was being set during this time, determined by the weak nuclear force interactions that converted one into the other. This ratio, roughly 7 protons for every neutron, would determine how much hydrogen and helium the universe would contain when nuclear fusion began minutes later. The first second of cosmic history contained the emergence of all four fundamental forces, the creation of all types of fundamental particles, the inflationary expansion that set the universe's large-scale structure, and the formation of protons and neutrons. Each of these events could fill books with detailed physics. Yet they all happened in less time than it takes for a human heart to beat once. The universe transformed from a state beyond description to something recognizable as a hot, expanding cosmos, still exotic, but now amenable to physics as we understand it. The groundwork for everything that would follow, stars, planets, life, was laid in this single extraordinary second. The temperature and density at 1 second, though extreme by our standards, were modest compared to what came before, and would drop rapidly as expansion continued through the minutes that followed. Photons filled the universe with light, but this light could not travel freely because electrons scattered it constantly, making the cosmos opaque, like a brilliant fog. The universe glowed with a light that could not propagate, could not carry information from one place to another, could not reveal what lay beyond nearby regions. This state would persist for hundreds of thousands of years, but before that, another crucial event awaited: the brief window when nuclear fusion could occur. The first second stands alone in cosmic history as the most event-filled single unit of time the universe has ever known or ever will know, a concentration of transformation unmatched by any era before or since. What took 1 second to accomplish in terms of physical changes would take billions of years to remotely approach again in the slower evolution that followed. The universe had sprinted through its infancy and was about to enter a brief childhood, the few minutes when atomic nuclei would form, before settling into the long, patient epochs that would occupy most of its existence. The story of that nuclear childhood begins now, in the minutes immediately following that remarkable first second. The universe at 1 second old was filled with protons, neutrons, electrons, and vast numbers of photons, all existing in a state too hot and too dense for atomic nuclei heavier than hydrogen to form. Protons are simply hydrogen nuclei, the simplest nucleus possible, a single positive charge. So hydrogen existed from the moment protons formed in that first second. But helium and heavier elements required neutrons and protons to combine and stay combined, which could not happen while temperatures remained high enough to blast apart any nucleus that tried to form. The universe needed to cool further. Before nucleosynthesis, the building of nuclei, could begin, and this cooling was happening rapidly as space expanded. The window for Big Bang nucleosynthesis opened at about 1 second and closed by about 3 minutes, giving the universe only a brief opportunity to forge elements heavier than hydrogen from its primordial ingredients. This narrow window existed because the process required temperatures hot enough for nuclear fusion, but cool enough for the fusion products to survive, rather than being immediately torn apart. The universe was cooling rapidly, passing through the sweet spot where fusion could work, and by 3 minutes, the temperature had dropped below what fusion requires. After 3 minutes, nuclear reactions essentially stopped, and the composition of the universe was locked in for the next several 100 million years. During this brief period, neutrons and protons combined to form deuterium first, the simplest step up from plain hydrogen, containing 1 proton and 1 neutron bound together. Deuterium then combined with more protons or neutrons to form helium-3, and helium-3 combined with itself, or with deuterium to form helium-4, the stable form of helium we know today. The chain of reactions moved quickly through these steps, converting most available neutrons into helium-4 within these few furious minutes of cosmic chemistry. Some lithium was also formed, the third element on the periodic table, but only in trace amounts, far less than hydrogen or helium. The final composition after nucleosynthesis ended was approximately 75% hydrogen and 25% helium by mass, with tiny traces of lithium and essentially nothing heavier. This composition would remain unchanged for hundreds of millions of years, until the first stars formed and began forging heavier elements in their cores. The ratio was determined by the number of neutrons available and the efficiency of the reactions that incorporated them into helium before they could decay. Free neutrons are unstable, decaying into protons in about 15 minutes if left alone. So the nucleosynthesis window closed partly because remaining neutrons were disappearing through decay. The remarkable thing about this primordial composition is that we can observe it today, measuring the abundances of hydrogen and helium in ancient gas clouds that have remained relatively unchanged since the universe was young. These measurements match the predictions of Big Bang nucleosynthesis with impressive precision, providing strong evidence that we understand what happened in those first few minutes. The match between theory and observation is one of the key pieces of evidence supporting the Big Bang model of cosmic history and our understanding of nuclear physics. When we see ancient hydrogen and helium in the ratios predicted, we are seeing the composition set in those first 3 minutes. Why did nucleosynthesis stop at helium and lithium rather than building heavier elements like carbon, oxygen, or iron that we know stars produce? The answer lies in a peculiarity of nuclear physics. There are no stable nuclei with 5 or 8 particles, creating gaps that the fusion process could not bridge under Big Bang conditions. After forming helium-4 with its 4 particles, the next step would require adding another proton or neutron to make a 5-particle nucleus. But such nuclei fall apart almost instantly. In stars, this problem is solved through a slower, more patient process involving multiple particles colliding simultaneously. But the rapid cooling of the early universe did not allow time for such unlikely events. The 3-minute window thus established a universe of hydrogen and helium, simple ingredients that would need billions of years of stellar cooking to produce the diversity of elements we see today. Every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in your blood was forged later inside stars through processes that the early universe could not manage. The Big Bang built the basic fuel, hydrogen for stars to burn, helium as a byproduct, and future fuel for later burning stages, but left the complex chemistry for later epochs. The periodic table would fill in slowly, star by star, supernova by supernova, across billions of years of cosmic evolution. By the time nucleosynthesis ended at about 3 minutes, the universe had expanded and cooled considerably from its state at 1 second, though it remained extraordinarily hot and dense by any standard we can relate to directly. The temperature was around 1 billion degrees, falling from 10 billion degrees at 1 second, and the density had dropped correspondingly as space stretched and matter spread thinner. Photons still dominated the energy content of the universe, outnumbering particles of matter by about 1 billion to 1. filling space with radiation that we would eventually detect as the cosmic microwave background. The universe at 3 minutes was a plasma of hydrogen nuclei, helium nuclei, free electrons, and photons, all mixed together in a state that would persist for hundreds of thousands of years. The photons in this plasma could not travel freely because electrons scattered them constantly, bouncing them in random directions every time they encountered an electron in their path through the hot, ionized gas. This scattering made the universe opaque, like a fog so thick you cannot see your hand in front of your face. Except the fog was brilliant rather than dim. The universe glowed with trapped light that could not propagate, could not carry information from one region to another, could not reveal the structure developing as matter, slowly gathered under gravity. This cosmic fog would persist until the universe cooled enough for electrons to bind to nuclei, an event still hundreds of thousands of years in the future. The 3-minute mark represents the end of the nuclear age of the early universe, the closing of the only window when nuclear reactions could occur until stars eventually ignited hundreds of millions of years later. After 3 minutes, the universe was a slowly cooling plasma where nothing much happened in terms of chemistry or nuclear physics, just expansion and cooling and the patient gathering of matter under gravity. The drama of the first second and the furious chemistry of the first 3 minutes gave way to a longer, quieter era that would test the patience of any observer who might have existed. The universe had established its basic ingredients and was now simply waiting for conditions to allow the next phase of its story to begin. The elemental abundances locked in during these first 3 minutes carry information about conditions in the early universe that we can decode through careful observation and comparison with theoretical predictions and calculations. The exact ratios of hydrogen to helium to lithium depend on factors like the density of protons and neutrons, the expansion rate of the universe, and the properties of neutrinos and other particles present. By measuring these ratios in ancient, pristine gas and comparing them to predictions, we can test our models of the early universe and constrain the properties of particles and forces. This cosmic consistency check has been performed many times and continues to support the standard picture of Big Bang nucleosynthesis. The universe, after 3 minutes, was committed to a long wait, a period that would last until nearly 400,000 years after the Big Bang, when temperatures finally dropped low enough for a crucial transition to occur. During this long era, the plasma slowly cooled, matter slowly gathered, but nothing visible happened because light could not escape the fog. The photons that would eventually become the cosmic microwave background were being constantly scattered, unable to travel, encoding no information about structure. This era of cosmic fog, lasting from 3 minutes to 380,000 years, represents the next chapter in our journey through cosmic time. The universe between 3 minutes and 380,000 years was a place of patient waiting, a hot plasma of hydrogen nuclei, helium nuclei, free electrons, and photons filling all of space in a slowly cooling mixture. Nothing visible was happening. No stars, no galaxies, no structures forming that we could see. Just this plasma, expanding and cooling and glowing with light that could not escape its own brilliance. The photons that filled space were constantly scattering off free electrons, bouncing in random directions, unable to travel in straight lines for any significant distance through the cosmic medium. This scattering made the universe opaque, a fog of light so thick that no information could propagate from one region to another. The state of matter in this era was similar to the interiors of stars today, where temperatures are high enough to ionize atoms and create a plasma of free nuclei and electrons. The universe at 10,000 years old was about 100,000 degrees hotter than the surface of any star, gradually cooling as expansion stretched the fabric of space and diluted the energy content. At 100,000 years, the temperature had dropped to perhaps 10,000 degrees, approaching the surface temperature of hot blue stars, the plasma beginning to approach conditions where electrons might finally bind to nuclei. The cooling was inexorable, driven by the expansion of the universe, bringing the cosmos slowly toward the moment when atoms could finally form. Throughout this era, gravity was gently working on the matter, distributed through space, pulling slightly denser regions toward themselves, and making them denser still over the thousands of years that passed. These density variations were tiny, just parts per 100,000, but they represented the seeds of all future cosmic structure, planted during inflation and now slowly growing under gravitational attraction. The dark matter that made up most of the universe's mass was particularly important here, gathering into structures before ordinary matter could follow, creating gravitational wells that would later collect gas and form stars. This slow gathering was invisible during the plasma era, but essential for everything that would come after. The light that filled the universe during this era was not organized into distinct sources, but spread uniformly everywhere, a cosmic glow that would have been visible from any location in space. If an observer could have existed in this plasma, they would have seen brightness in every direction, no darkness anywhere, a universe filled with light that had nowhere to go. The color of this light shifted as the universe cooled, starting white hot and gradually reddening as temperatures dropped, though it remained far too bright and hot for any material structures to exist. This was not the light of stars or galaxies, but primordial light, the afterglow of the Big Bang itself, still trapped in the cosmic fog. The composition of the plasma remained fixed throughout this era. The hydrogen and helium ratios established in the first 3 minutes, persisting unchanged through hundreds of thousands of years of passive cooling. No nuclear reactions could occur at these temperatures. Too cool for fusion, too hot for chemistry, leaving the elemental abundances locked in their primordial state. The plasma was electrically neutral overall, with exactly as many electrons as protons, plus twice the number of helium nuclei. But those electrons remained free rather than bound to nuclei. This free state of the electrons was what made the universe opaque, their constant scattering of photons preventing light from traveling freely. As the universe approached 380,000 years old, temperatures dropped toward 3,000 degrees, the critical threshold below which electrons would finally be able to bind to nuclei and form neutral atoms. This temperature is special because it represents the ionization energy of hydrogen below 3,000 degrees. The average photon does not carry enough energy to knock an electron out of a hydrogen atom. Above this temperature, atoms cannot survive because photons constantly ionize them. Below it, atoms can form and remain stable against the photon bombardment. The universe was approaching this threshold with each passing millennium. The transition from ionized plasma to neutral atoms is called recombination. though the name is slightly misleading since the electrons had never been combined with nuclei before. This was their first time forming atoms. The process did not happen instantaneously, but occurred over a span of perhaps 80,000 years as the universe cooled through the critical temperature range where ionization and recombination competed. As more and more electrons bound to nuclei, the universe became increasingly transparent, photons finding fewer free electrons to scatter from and beginning to travel farther before interactions. The fog was clearing, and light was beginning to stream freely through space for the first time. At 380,000 years, the transition was essentially complete, and the universe had transformed from an opaque plasma into a transparent gas of neutral hydrogen and helium atoms. The photons that had been trapped in the plasma were suddenly free to travel through space without scattering, streaming in straight lines across the universe for the first time since they were created. These photons are still traveling today, stretched by the expansion of the universe from their original visible wavelengths into microwaves, forming the cosmic microwave background radiation we detect with radio telescopes. Every direction we look, we see these ancient photons, the oldest light in existence, released when the universe became transparent. The cosmic microwave background is the earliest snapshot we can see of the universe, a picture of the cosmos at 380,000 years old, with every earlier era hidden behind the opacity of the primordial plasma. The tiny temperature variations in this ancient light, parts per 100,000 warmer or cooler in different directions, reveal the density fluctuations that existed in the plasma before recombination. These fluctuations grew into the galaxies and galaxy clusters we see today. And by mapping the microwave background, we can see the seeds from which all cosmic structure grew. The patterns in this light have been studied intensively, teaching us about the composition, age, and geometry of the universe. The release of the cosmic microwave background marked the end of the plasma era and the beginning of something new, a universe of neutral atoms where matter and light no longer interacted as strongly as before. For the first time, matter could move without dragging radiation along with it, and light could travel without being constantly deflected by interactions with matter. This decoupling of matter and radiation allowed structures to grow more freely under gravity, though the growth remained slow in these early times, before stars provided new sources of heat and light. The universe at recombination was dark in a new way, not the darkness of opacity, but the darkness of an absence of light sources. The photons released at recombination carried away the glow that had filled the universe since the Big Bang, leaving behind a cosmos that was, for the first time, capable of true darkness. The neutral gas that filled space was not glowing. It had no internal energy source to produce light, and the cosmic microwave background photons were streaming away into the expanding future. For the next 200 million years, the universe would be dark, lit only by the fading afterglow of recombination that redshifted further from visibility with each passing eon. This period, from recombination to the ignition of the first stars, is called the Cosmic Dark Ages, and it represents a chapter of cosmic history that remains largely unobserved. The moment of recombination was a pivot in cosmic history, a transition from the hot, bright, opaque youth of the universe to the cool, dark, transparent conditions that would allow structures to form and eventually produce the light of stars. The universe, at 380,000 years, was a far cry from the universe at 1 second. Yet both were steps in the same unfolding story of cosmic evolution. The primordial plasma had served its purpose, carrying the universe from its earliest moments through the nucleosynthesis era to the point where atoms could form and light could escape. Now a new era was beginning, an era of darkness and patient waiting. The universe, after recombination, was dark in a way that nothing in our experience can approximate, a darkness more complete than any night sky we have ever seen. No stars existed anywhere in the cosmos, no galaxies, no sources of visible light at all, just vast clouds of neutral hydrogen and helium drifting through expanding space. The cosmic microwave background was fading and redshifting, its photons still traveling, but stretching toward longer wavelengths that moved them out of the visible spectrum into the infrared and beyond. This was the cosmic dark age, an era lasting from 380,000 years to roughly 200 million years after the Big Bang. The darkness was not inactive darkness. Things were happening in the shadows, even though no light existed to reveal them to any potential observer. Gravity continued its patient work, pulling matter toward denser regions, amplifying the tiny fluctuations that had been imprinted during inflation and revealed in the cosmic microwave background. Dark matter, which does not interact with light and therefore was unaffected by the fog of the plasma era, had a head start in this gravitational gathering. It had been clumping since long before recombination, creating invisible scaffolding that ordinary matter would now fall into and collect upon. The role of dark matter in structure formation was essential, providing the gravitational wells where gas would eventually collect and form the first stars and galaxies. Without dark matter, the ordinary matter would have taken much longer to gather into dense enough clumps, and the cosmic story would have unfolded far more slowly. The fluctuations in ordinary matter, visible in the cosmic microwave background, were small, but the dark matter fluctuations were larger and deeper, having grown without the pressure resistance that light provided to ordinary matter. Ordinary matter now fell into these pre-existing dark matter structures, like rain-filling valleys carved by earlier erosion. The gathering was slow by any standard we can relate to, taking millions of years to produce density contrasts that were still subtle by everyday measures. Gas clouds that would eventually become the first stars were still diffuse, spread across regions that spanned what would eventually be thousands of light years in our modern reckoning of distance. The temperatures were low, just a few tens of degrees above absolute zero, and the densities were far below the best vacuums we can produce in laboratories on Earth. Yet compared to the surrounding space, these regions were dense, gravitationally bound, and slowly contracting toward the moment when pressure and temperature would rise enough to ignite nuclear fusion. The physics of this era is relatively simple compared to the frantic activity of the first second, or the complex chemistry that would eventually develop once stars existed and elements diversified. Gravity pulled matter inward. Pressure resisted this pull. Radiation carried away energy and allowed contraction to continue. Eventually, the centers of contracting clouds became hot and dense enough for fusion. The process required patience on scales that dwarf human experience, millions of years passing as clouds slowly condensed towards stellar ignition. An observer in this era would have seen nothing changing, the darkness persisting, without any sign that the most dramatic transformation since the Big Bang was approaching. The absence of heavy elements made the physics of this era different from later star formation, which would benefit from the cooling properties of carbon, oxygen, and other elements that radiate heat efficiently. The primordial gas was hydrogen and helium only, which cool poorly compared to heavier elements, meaning that clouds had to be more massive and collapse had to be more dramatic to achieve the temperatures needed for fusion. The first stars, when they formed, would be monsters, hundreds of times more massive than our Sun, because only such large masses could overcome the cooling limitations of pure primordial gas. These giant stars would burn fast and die young, their brief lives ending in explosions that would seed the universe with the first heavy elements. The 21-centimeter radiation from neutral hydrogen offers one potential window into the dark ages, a faint signal that hydrogen atoms emit when their electrons flip between two subtly different energy states. This radiation passes through the fog that blocked light during the plasma era, potentially carrying information about the dark ages to us across billions of years of cosmic expansion. Detecting this signal is extraordinarily difficult because it is faint and has been redshifted to much longer wavelengths by the expansion of the universe, requiring special radio telescopes designed for this specific purpose. Experiments are underway to detect this primordial hydrogen signal and peer into the dark ages that preceded cosmic dawn. The duration of the cosmic dark ages, roughly 200 million years, seems long by human standards, but was brief compared to the nearly 14 billion year history of the universe we are exploring tonight. This era represented less than 2% of cosmic history, a relatively short interlude between the drama of the Big Bang and the drama of the first stars. Yet it was a necessary interlude, a time when gravity did its work of gathering matter and preparing the conditions for the luminous universe that would follow. Without this patient preparation, stars could not have formed, and the cosmos would have remained a diffuse, uniform gas, forever expanding into an empty future. As we approach the end of the Dark Ages, around 200 million years after the Big Bang, the densest regions of gathering gas were approaching the critical conditions needed for nuclear ignition. The centers of the largest, most massive clouds had compressed and heated to temperatures of millions of degrees, approaching the threshold where hydrogen nuclei could overcome their electrical repulsion and fuse. The pressure at these centers was enormous, the density far exceeding anything that had existed since the first seconds after the Big Bang, conditions building toward the moment when fusion would begin. The universe was about to emerge from its longest darkness. The end of the Dark Ages was not a single moment, but a gradual dawning. As different regions achieved stellar ignition at slightly different times, depending on their initial density and their history of gravitational collapse. The first star to ignite was likely not alone, but one of many forming around the same cosmic epoch. Different regions reaching the threshold within a relatively narrow window of cosmic time. Once the first stars ignited, their light began traveling through the darkness. The first new photons since the cosmic microwave background was released hundreds of millions of years earlier. The cosmic dawn was breaking, and the universe was about to enter a new era of light. The transition from Dark Ages to cosmic dawn represents one of the great turning points in cosmic history, the moment when the universe went from passive cooling and gravitational gathering to active energy generation through nuclear fusion. Before the first stars, the universe was slowly running down, its energy spreading thinner as space expanded, nothing creating new sources of light or heat. After the first stars, the universe became a factory of energy and elements, constantly creating new things through processes that would eventually lead to planets, chemistry, and life. The Dark Ages were ending, and the luminous universe was about to begin its long career. The first star to ignite anywhere in the universe did so in complete darkness, a single point of light appearing where no light had existed for 200 million years. The first new photon source since the cosmic microwave background was released. We do not know exactly when or where this happened, cannot point to a specific location or moment, but the physics tells us that around 200 million years after the Big Bang, conditions in the densest regions had finally reached the threshold for nuclear fusion. The core of a collapsing gas cloud, compressed by gravity and heated by that compression, achieved temperatures of millions of degrees and densities where hydrogen nuclei could fuse into helium. A star was born, the first of trillions upon trillions that would eventually light the cosmos. These first stars are called population 3 stars, a name that reflects the order in which astronomers discovered the different stellar generations. Population 1 being stars like our Sun, population 2 being older metal-poor stars, population 3 being the hypothetical primordial first generation. We have never directly observed a population 3 star because they all died billions of years ago, their lives too brief for any to survive to the present day. Everything we know about them comes from theoretical models and simulations, calculations of what must have happened based on the physics of gas, composed only of hydrogen and helium. These models tell us that population 3 stars were giants, typically hundreds of times more massive than our Sun. The reason for their enormous size lies in the cooling limitations of primordial gas, which lacked the heavy elements that allow modern gas clouds to radiate heat efficiently and fragment into smaller clumps. Heavy elements like carbon and oxygen have many energy levels that can be excited by collisions and then emit photons, carrying away energy and allowing the gas to cool and compress further. Hydrogen and helium are much simpler atoms with fewer ways to radiate, meaning they trap heat more effectively and resist the compression that leads to star formation. Only the most massive collapsing regions could overcome this resistance and achieve stellar ignition, producing stars far larger than any that form today. A star with 100 solar masses burns with extraordinary ferocity, its surface temperature far exceeding our Sun's, its luminosity perhaps 1,000,000 times greater, its core consuming fuel at rates that cannot be sustained for long. Such a star might live only a few million years, a cosmic eye blink compared to the 10 billion year lifetime of a sun-like star, before exhausting its fuel and reaching the end of its nuclear burning life. The death of such a massive star would be spectacular. Either a supernova explosion that scattered its outer layers across space, or a direct collapse into a black hole that swallowed everything forever. Either fate would have profound consequences for the cosmic environment. The light from the first stars did more than simply illuminate the darkness. It began transforming the chemical state of the universe's gas through a process called reionization. The intense ultraviolet radiation from these hot, massive stars carried enough energy to strip electrons from hydrogen atoms, reversing the recombination that had made the universe transparent at 380,000 years. Around each first-generation star, a bubble of ionized gas formed, growing as the star's radiation penetrated further into the surrounding neutral hydrogen. These ionized bubbles grew and eventually merged, slowly transforming the universe from neutral to ionized once again. Reionization was not instant, but occurred over hundreds of millions of years as more and more stars formed and their combined radiation ionized larger and larger volumes of space. The process was probably patchy, with some regions ionizing earlier than others, depending on how many stars had formed there, creating a cosmic landscape of ionized bubbles, separated by neutral regions that slowly shrank. By about 1 billion years after the Big Bang, the process was essentially complete, and the universe had transitioned to the ionized state it maintains today, where most of the hydrogen between galaxies exists as individual protons and electrons rather than neutral atoms. This transition is sometimes called the end of the cosmic dark ages. Though the first light appeared much earlier, the deaths of population 3 stars were as important as their lives, because these deaths created and scattered the first heavy elements, everything heavier than helium, throughout the surrounding gas. Before these first supernovae, no carbon existed anywhere in the universe. No oxygen, no iron, no silicon, nothing from which rocky planets could ever form. The explosions of massive stars created these elements through nuclear processes in the final moments before and during the explosion, then scattered them across light years of space. This seeding of heavy elements, called chemical enrichment, transformed the raw materials available for subsequent star formation. The next generation of stars, forming from gas that had been enriched by population 3 supernovae, would be different, smaller, longer-lived, more diverse in their properties because the heavy elements changed the physics of star formation. These population 2 stars could form in smaller masses because carbon and oxygen cooling allowed gas to fragment into smaller clumps, producing stars ranging from much smaller to somewhat larger than our Sun. They lived longer, burned more steadily, and when they died, they added further to the heavy element content of the surrounding gas. Each stellar generation built on the chemical legacy of its predecessors. The first few 100 million years of cosmic luminosity were a time of rapid transformation. The universe going from complete darkness to scattered points of light to an increasingly populated cosmic landscape of stars and proto-galaxies. The transition was not smooth or uniform, but varied from region to region, depending on local density and the history of gravitational collapse in each area. Some regions lit up earlier, others remained dark longer. Gradually, the darkness retreated as more and more of space became illuminated by stellar radiation. The universe was waking up, star by star, across hundreds of millions of years of cosmic dawn. By 500 million years after the Big Bang, the first recognizable galaxies were beginning to form from the merging of smaller stellar groups, collections of millions or billions of stars bound together by gravity and dark matter. These early galaxies were not the grand spirals we see today. They were irregular, clumpy, actively forming stars at rates far exceeding modern galaxies, their shapes disturbed by frequent mergers with neighboring collections. The hierarchical process of structure formation was underway, small objects merging into larger ones merging into larger still, building the cosmic architecture that would define the universe for billions of years. The era of cosmic dawn was transitioning into the era of galaxy formation. The first galaxies were nothing like the elegant spirals that populate coffee table astronomy books, those symmetric pinwheels of stars and dust that seemed to hang motionless against the black backdrop of space. Instead, they were chaotic, irregular, clumpy collections of stars and gas, constantly colliding and merging with neighboring objects, their shapes distorted by gravitational interactions that never seemed to cease. These early galaxies formed through the hierarchical assembly of smaller structures, stellar clusters, and protogalactic fragments falling together under gravity and merging into larger composite objects. The process was messy, violent by cosmic standards, and would continue for billions of years as small structures combined into larger ones. The universe, between 500 million and 1 billion years after the Big Bang, was filled with these irregular early galaxies, scattered through space like islands in a vast ocean, separated by enormous distances that were still growing as the universe expanded. Each galaxy was an active construction site, converting gas into stars at rates that would not be matched again in cosmic history. The raw materials of stellar formation still abundant and readily available. Stars formed in bursts, triggered by mergers and gas compression, producing stellar populations in episodic waves rather than the steady trickle we see in mature galaxies today. These galaxies were young and vigorous, burning through their resources with the heedless intensity of cosmic adolescence. The light from these early galaxies carried the ultraviolet radiation that was completing the reionization of the universe, each galaxy contributing to the growing network of ionized bubbles that would eventually fill all of intergalactic space. The more massive and actively star-forming galaxies contributed most to this process, their hot young stars pumping out ionizing photons that stripped electrons from hydrogen atoms across millions of light years. As the bubbles grew and merged, the universe became increasingly transparent to certain wavelengths of light that had been absorbed by neutral hydrogen, opening new windows for cosmic observation. By 1 billion years, reionization was essentially complete, and the universe had achieved the ionized state it maintains today. The transition from neutral to ionized intergalactic medium marked an important change in the cosmic environment, affecting how light traveled and how gas behaved in the spaces between galaxies. Neutral hydrogen absorbs certain wavelengths of light very efficiently, creating dark bands in the spectra of distant objects that reveal the presence and distribution of this gas along the line of sight. After reionization, the intergalactic medium became largely transparent, allowing light to travel more freely across cosmic distances without being absorbed by intervening neutral gas. The universe at 1 billion years was more open, more transparent, more amenable to the astronomical observation that would eventually allow creatures like us to study it. The growth of galaxies continued through the first billion years and beyond, with smaller objects merging into larger ones and gas flowing into established galaxies from the surrounding intergalactic medium. This gas inflow provided raw material for continued star formation, feeding the galaxies even as they converted existing gas into stars at prodigious rates. The balance between gas consumption through star formation and gas replenishment through inflow determined how long galaxies could maintain their high star formation rates before running low on fuel. Some galaxies would eventually exhaust their gas and stop forming new stars, becoming what astronomers call quiescent or dead galaxies. Supermassive black holes, objects containing millions to billions of solar masses, were already growing in the centers of early galaxies, fed by gas that fell toward the gravitational centers of these assembling structures. Some of these black holes became quasars, the most luminous objects in the early universe, outshining their host galaxies by factors of hundreds, as matter falling into them released tremendous energy. Quasars from this era are among the most distant objects we have detected, their light traveling for more than 12 billion years to reach our telescopes, showing us the universe as it was when it was less than 1 billion years old. These beacons from the early universe provide crucial information about conditions in the cosmic youth. The relationship between black holes and their host galaxies was already being established in this early era, a relationship that persists today and seems to reflect some fundamental connection between how galaxies form and how their central black holes grow. The mass of a galaxy's central black hole correlates with properties of the galaxy itself, particularly the mass of the stellar bulge at the galaxy's center, suggesting that the two grew together in some coordinated fashion. Whether the black hole influences the galaxy, or the galaxy influences the black hole, or both influence each other, remains an active area of research, with the early universe providing crucial testing grounds for competing theories. The cosmic web, the large-scale structure of the universe consisting of filaments, nodes, and voids, was becoming increasingly defined during this era as matter continued to flow along the scaffolding created by dark matter, gravitational attraction. Galaxies were not randomly distributed, but concentrated along filaments where matter had gathered, with the densest concentrations at the intersections of filaments where galaxy clusters would eventually form. Between the filaments lay vast voids, regions where matter had drained away toward the denser structures, leaving nearly empty space that would become more empty still as expansion continued. This cosmic architecture was set during the early universe and would persist for all subsequent time. The universe at 1 billion years was a busy, active place, filled with young galaxies, growing black holes, ongoing reionization, and the constant merger and growth of cosmic structures at all scales. Yet compared to what would come later, it was still an early draft, a rough sketch of the mature cosmos that would eventually develop through billions of additional years of evolution. The galaxies were smaller, the heavy element content lower, the stars more primitive in their composition. Everything was still under construction. The universe had emerged from its dark ages and established the basic framework of cosmic structure. But the great work of building the modern cosmos was just beginning. The universe between 1 and 4 billion years after the Big Bang reached its peak rate of cosmic star formation, an era sometimes called cosmic noon, when more stars were being created per year than at any other time in the history of the cosmos. This was the Great Construction Era, when galaxies were converting their gas reserves into stellar populations with an efficiency and urgency that would never be matched again, building much of the stellar mass that exists in the universe today. The conditions that made this era so productive would eventually pass. Gas supplies would dwindle, and star formation rates would decline toward the relatively sleepy levels we observe in the modern universe. But for these few billion years, the cosmos was in full bloom. The galaxies of cosmic noon were different from modern galaxies in several important ways, reflecting their youth and the abundant gas supplies that fueled their intense star formation activity. They were clumpier, their structures less organized into the smooth disks and bulges that characterize mature spiral galaxies. Their shapes often disturbed by ongoing mergers and interactions with neighboring galaxies. The stars they produced were forming in dense clusters and associations, bursting forth in episodes triggered by gas compression, rather than in the steady, distributed manner of modern star formation. These galaxies were vigorous, almost frantic in their activity, burning through their resources in a cosmic blaze of stellar production. The star formation rate of the universe as a whole peaked at around 2 to 3 billion years after the Big Bang, with roughly 10 times as many stars forming per year as form today in the same volume of space. This peak reflected the balance of several factors. Gas supplies were still abundant, having not yet been consumed by earlier generations of star formation. Galaxies had grown large enough to form stars efficiently, and the merger rate remained high, triggering starbursts through gas compression during galaxy collisions. After this peak, all these factors began working against continued high star formation. Gas was consumed. Galaxies grew more isolated as expansion carried them apart. And the cosmic construction era gave way to a slower era of decline. The heavy element content of the universe was increasing rapidly during cosmic noon, as each generation of stars lived, died, and scattered its nuclear-processed materials back into the interstellar medium from which new stars would form. The first stars had been pure hydrogen and helium. By cosmic noon, the gas forming new stars might be 1 or 2% heavy elements, still low by modern standards, but enough to change the physics of star formation significantly. This enrichment allowed smaller stars to form more easily, diversifying the stellar population and extending the average stellar lifetime beyond what the massive early stars could achieve. The cosmic inventory of elements was filling in, approaching the composition needed for rocky planets and complex chemistry. Galaxy mergers during cosmic noon were frequent and transformative events, occurring when the paths of neighboring galaxies crossed and their mutual gravity drew them into increasingly close encounters. These encounters triggered intense bursts of star formation, as gas clouds compressed during the interaction, lighting up both galaxies with the blue glow of hot young stars, forming in vast numbers. The mergers also fed the central black holes of the colliding galaxies, gas losing angular momentum and falling toward the gravitational centers where it could be consumed and converted to the tremendous luminosities of quasars. Some of the brightest objects in the early universe were these merger-driven phenomena, visible across billions of light years. The quasars of cosmic noon were among the most luminous objects the universe has ever produced. Single points of light, outshining entire galaxies of hundreds of billions of stars through the release of gravitational energy by matter falling into supermassive black holes. These black holes were growing rapidly, consuming gas at rates that added millions of solar masses to their totals in relatively short cosmic times, building toward the massive black holes that lurk in the centers of galaxies today. The quasar era peaked around the same time as cosmic star formation, suggesting a connection between the growth of black holes and the growth of stellar populations in their host galaxies. Both were fed by the same abundant gas supplies that characterized this active cosmic epoch. The relationship between black hole growth and star formation remains one of the interesting puzzles of galaxy evolution, with observations suggesting that the two processes are somehow linked despite occurring at very different scales within galaxies. One possibility is that both are fed by the same gas inflows, so that conditions favoring one naturally favor the other through common fuel supplies. Another possibility is that the black hole's activity regulates star formation in its host galaxy, either triggering it through compression or suppressing it through heating of the surrounding gas. This so-called feedback between black holes and their galaxies may explain the correlations we observe and the eventual decline of star formation as galaxies mature. By 4 billion years after the Big Bang, cosmic noon was ending, star formation rates were declining, and the universe was transitioning toward the calmer conditions of its modern era, a decline that would continue for the next 9 billion years to the present. Gas supplies were becoming exhausted as earlier generations of star formation consumed the raw materials, and the cosmic expansion was carrying galaxies farther apart, reducing the merger rate that had triggered so much activity. Galaxies were settling into their mature forms, developing the organized structures of spiral arms and bulges that would characterize them for the remainder of cosmic history. The Great Construction Era was giving way to the long afternoon of cosmic evolution. The universe, at 4 billion years, contained most of the stellar mass that would ever exist. The subsequent 9 billion years, adding relatively little to the cosmic stellar inventory compared to what had been built during cosmic noon. This counterintuitive fact that most stars were built when the universe was young, rather than accumulating steadily over time, reflects the declining gas supplies and merger rates that characterized the post-noon era. The universe was not finished evolving, and important things would continue to happen, but the explosive growth of the construction era was behind it. What remained was the slower work of refinement and development. The Milky Way, our home galaxy, was one of the billions of galaxies taking shape during the construction era, assembling from smaller components and growing through mergers that added mass and complexity to its developing structure. The galaxy that would eventually contain our solar system was not born as a unified whole, but built piece by piece, smaller galaxies falling together over billions of years, their stars and gas combining into an ever larger composite object. By 4 billion years after the Big Bang, the Milky Way was already a substantial galaxy, though still actively growing and different in important ways from its present form. The next 5 billion years would see it settle into maturity. The oldest stars in the Milky Way date from these early times, metal-poor objects orbiting in the galactic halo that surrounds the disk where younger stars like our Sun reside. These ancient stars are survivors from the galaxy's youth, formed when heavy element abundances were still low and stellar populations were still primitive by modern standards. Their orbits are often highly elliptical, carrying them far above and below the galactic plane, reflecting the chaotic motions of the early galaxy before it settled into its current organized rotation. Studying these stars gives us windows into the galaxy's past, fossils of an era we cannot otherwise observe directly. The disk of the Milky Way the flattened plane where our Sun and most familiar stars reside, formed more gradually as gas settled into a rotating structure around the galactic center. This settling required the gas to lose energy through radiation, allowing it to sink toward the lowest energy configuration, a thin, rotating disk oriented perpendicular to the axis of rotation. Stars forming within this disk inherited its rotation, orbiting the galactic center in nearly circular paths that keep them confined to the plane throughout their lives. The disk structure we see today is the result of billions of years of this settling process, gas converting to stars, generation after generation, in the same flattened configuration. The spiral arms that give the Milky Way and similar galaxies their distinctive appearance are density waves propagating through the galactic disk, regions where gas and stars are slightly compressed compared to the spaces between the arms. These compressions trigger star formation, so the arms are traced by bright young blue stars that illuminate the spiral pattern despite being a small fraction of the total stellar population. The spiral pattern rotates around the galaxy at a different speed than the stars themselves orbit, so stars pass through the arms rather than residing permanently within them. This density wave theory explains why spirals persist for billions of years, despite the differential rotation that would otherwise wind them up and destroy them. Chemical enrichment continued throughout the Milky Way's history, each generation of stars adding to the heavy element content of the interstellar gas from which subsequent generations would form. The stars forming in the disk 4 or 5 billion years ago contained perhaps 1% heavy elements by mass, approaching the 2% or so found in the Sun and its contemporaries. This enrichment opened new possibilities for what could form alongside stars. The rocky cores of planets, the silicate mantles, the iron cores that would eventually characterize worlds like Earth. The chemical building blocks for complex worlds were accumulating in the galaxy's raw materials. Around 5 billion years ago, the Milky Way experienced its last major merger with a substantial galaxy, an event called the Gaia Sausage or Gaia Enceladus merger, based on the discovery of its remnants through precise stellar surveys. This merger added significant mass to the Milky Way's halo and thickened its disk, leaving streams of stars with distinctive chemical signatures and orbital patterns that we can still identify today among the galaxy's population. Since then, the Milky Way has been relatively undisturbed, absorbing only small dwarf galaxies that add little to its overall mass or structure. The galaxy entered its mature phase, settling into the stable configuration we observe today. The bar at the center of the Milky Way, an elongated structure of stars that rotates as a rigid body, probably formed sometime in the last few billion years as the disk became massive enough to become dynamically unstable to bar formation. This bar channels gas toward the galactic center, feeding the central regions and potentially triggering bursts of star formation in the nuclear region where gas accumulates. The central black hole, Sagittarius A star, containing about 4 million solar masses, grew to its present size through millions of years of sporadic feeding as gas, and occasionally, entire stars fell into its gravitational grasp. The galactic center remains the most extreme environment in our neighborhood of space. By 9 billion years after the Big Bang, 4.6 billion years before the present, the Milky Way had reached a state where one particular region of the disk contained gas enriched with sufficient heavy elements at the right temperature and density to form a solar system like ours. This region was not special by any cosmic standard, just one of countless similar star-forming regions distributed throughout the galaxy's spiral arms. But it happened to be the region where our sun and planets would form. The stage was set for a transition from cosmic history to local history, from the story of the universe to the story of our particular corner of it. The galaxy that hosted our solar system's birth was already old by the time our sun formed, containing stars dating back to the earliest epochs of its assembly, alongside the continuous production of new stars in the spiral arms. This mix of ages characterized the galactic disk, old stars mixed with young, ancient stellar populations, coexisting with recent arrivals in a single gravitationally bound system. Our sun, when it formed, was neither particularly old nor particularly young by the standards of galactic stellar populations, a middle-aged generation in a galaxy that had been forming stars for billions of years. The galaxy was our sun's context, the larger system within which our small corner of space found its place. 4.6 billion years ago, in a region of the Milky Way's disk that was neither special nor remarkable by any cosmic standard, a cloud of gas and dust began to collapse under its own gravity, initiating a process that would produce our sun and solar system. This cloud contained the accumulated products of billions of years of stellar evolution: hydrogen from the Big Bang, helium from the first 3 minutes and from subsequent stellar burning, and heavier elements from countless supernovae and stellar winds that had enriched the galactic medium. The raw materials for our solar system were ancient by the time they came together. Atoms that had existed in various forms since the early universe began synthesizing them from pure energy. The collapse may have been triggered by a nearby supernova, a shock wave compressing the cloud and initiating gravitational contraction that the cloud could not reverse once it began. We find evidence for this triggering event in the form of certain radioactive isotopes present in the oldest solar system materials. Atoms that could only have been produced in a supernova and incorporated into the collapsing cloud before they had time to decay. This supernova, if it occurred, provided both the trigger for our solar system's formation and some of the specific atomic ingredients that would become part of the sun and planets. We are, in this sense, children of that particular stellar death. The center of the collapsing cloud accumulated most of the mass, condensing into an ever denser core that heated as gravitational energy converted to thermal energy through compression. Over about 100,000 years, this central concentration grew into a protostar. Not yet hot enough for nuclear fusion, but already a distinct object with a surrounding disk of material that had not yet fallen into the center. The rotation of the original cloud prevented all the material from falling directly into the center, causing it instead to flatten into a disk that would become the birthplace of planets. This protoplanetary disk extended for hundreds of astronomical units, far beyond where the planets would eventually orbit. Within the disk, tiny grains of dust began sticking together through gentle collisions, building larger and larger particles in a process called accretion that would eventually produce planets. These grains were made of refractory materials, silicates and metal oxides that could survive the temperatures in the inner disk, and of ices in the colder outer regions where water and other volatile compounds could condense. The sticking process was slow at first, grains growing from micrometer sizes to millimeter sizes over thousands of years. But as particles grew larger, they could capture smaller particles more efficiently. The disk was slowly transforming from gas and dust into the building blocks of worlds. Around the young sun, temperatures varied dramatically with distance, creating zones where different materials could condense from the gas and participate in planet formation. Close to the sun, within about 4 astronomical units, only rocky materials could survive, the temperatures too high for ices to remain solid. Beyond this frost line, water ice became stable, adding to the solid material available for planetary growth and enabling the formation of much larger bodies. This temperature gradient explains the basic architecture of our solar system. Small rocky planets close in, giant planets rich in ices and gas further out. The gas giants, Jupiter and Saturn, formed through a 2-stage process, first accumulating rocky and icy cores through accretion, then capturing enormous atmospheres of hydrogen and helium from the disk gas once their cores grew massive enough. This atmospheric capture had to happen quickly, before the disk gas was dissipated by the young sun's radiation and stellar wind, which typically removes disk gas within a few million years. Jupiter's core apparently reached the critical mass for rapid gas capture first, allowing it to become the largest planet, while Saturn's slightly later development left it second in size. Uranus and Neptune formed later still, accumulating less gas before the disk dispersed. The rocky planets, Mercury, Venus, Earth, and Mars, formed more slowly and never reached the mass needed to capture significant atmospheres from the disk, remaining as solid bodies with thin atmospheres outgassed from their interiors or delivered by later impacts. Their formation involved the collision and merger of countless smaller bodies called planetesimals, objects ranging from kilometers to hundreds of kilometers in size that represented the intermediate stage between dust grains and full-sized planets. These collisions were violent, converting kinetic energy to heat and melting the growing planets from the inside out as they accumulated mass. Earth's formation probably took about 100 million years, a long process of accumulating material through countless impacts. The final major impact in Earth's formation history was the collision with a Mars-sized body, sometimes called Theia, an impact so violent that it melted both bodies and ejected vast amounts of material into orbit around the Earth. This material coalesced to form our moon, the largest moon relative to its planet in the inner solar system, a companion that has influenced Earth's rotation, tides, and perhaps even the stability of its axis throughout geological history. The moon-forming impact happened about 50 million years after the solar system began forming, when Earth was already substantially assembled but still growing through occasional giant impacts. By 100 million years after the cloud collapse began, the basic architecture of our solar system was established. 8 major planets in orbits that would remain stable for billions of years. Dwarf planets and asteroids in the gaps and margins, and the leftovers of formations scattered through the outer reaches as comets and Kuiper belt objects. The solar system had emerged from its violent youth into a more settled configuration. Though the early heavy bombardment would continue for several 100 million years as leftover debris continued raining down on the planets and moons, this bombardment would prove crucial for Earth's development. The Earth that emerged from the solar system's formation was nothing like the planet we know today. A world of molten rock and continuous bombardment, its surface glowing with the heat of accretion and radioactive decay, its atmosphere thick with steam and volcanic gases. The moon-forming impact had left the planet entirely molten, and subsequent impacts continued delivering energy that kept the surface in a hellish state for hundreds of millions of years after the solar system's basic architecture was established. This was the Hadean Aeon, named after the Greek god of the underworld, a fitting designation for a world that resembled the traditional images of hell more than any paradise of life. As the rate of bombardment slowly declined and radioactive heating diminished, Earth's surface began to cool, a crust forming over the molten interior like ice forming on a winter pond, solidifying first and then gradually thickening over millions of years. The atmosphere, initially dominated by carbon dioxide, water vapor, and other volcanic emissions, began to cool as well, and at some point, perhaps around 4 billion years ago, temperatures dropped enough for water vapor to condense. Rain fell on the cooling crust, filling the lowest areas and forming the first oceans, bodies of water that have persisted in some form ever since, despite all the changes the planet has undergone. The early oceans were probably not like modern oceans, their chemistry different, their temperatures possibly higher, their depths perhaps uncertain as the surface continued to evolve and the bombardment continued adding material and energy. The atmosphere contained no free oxygen, the chemistry maintained in a reduced state that would be hostile to most modern life forms. Yet somehow, in these strange conditions, life emerged, the most profound transition in Earth's history, the moment when chemistry became biology and the planet began its long career as a living world. How this happened remains one of the greatest unsolved mysteries in science. The evidence for early life comes from rocks that have survived 4 billion years of subsequent geological history, ancient formations that contain chemical signatures, and structural fossils, suggesting that life existed almost as soon as conditions allowed. The oldest definite fossils are stromatolites, dating to about 3.5 billion years ago, layered structures created by microbial mats similar to those still forming in certain environments today. But chemical signatures in even older rocks suggest that life may have existed by 4 billion years ago, only a few 100 million years after the oceans formed, an astonishingly rapid emergence by geological standards. The first living things were almost certainly single cells, organisms without nuclei or complex internal structures, similar to the bacteria and archaea that still dominate Earth's biosphere today by sheer numbers and metabolic diversity. These early cells used chemical energy from their environment to sustain themselves and reproduce, probably deriving energy from chemical reactions involving compounds available in hydrothermal vents or sunlit, shallow waters. They contained the fundamental machinery of life: genetic information encoded in nucleic acids, proteins that catalyzed chemical reactions, membranes that separated inside from outside, though probably in simpler forms than their modern descendants. The origin of life required the emergence of self-replicating chemistry, molecules that could copy themselves and thereby persist across time, even as individual molecules were destroyed by chemical reactions and environmental stresses. How ordinary chemistry crossed this threshold into biology remains deeply uncertain, with competing theories proposing different environments and different chemical pathways for the transition. Some theories favor hydrothermal vents, where chemical gradients provide energy and mineral surfaces might catalyze key reactions. Others favor shallow ponds or beaches, where cycles of wetting and drying might concentrate reactants. The answer may involve environments and processes we have not yet considered. Whatever the mechanism, life established itself on Earth by about 4 billion years ago, and immediately began influencing the planet's chemistry and environment. A reciprocal relationship that has continued ever since. Life did not merely adapt to Earth's conditions, it changed those conditions, altering atmospheric chemistry, creating new minerals, transforming the global carbon cycle in ways that affected climate and surface conditions. The history of Earth after life's emergence is a history of co-evolution between life and planet, each shaping the other in an ongoing dance that has produced the world we inhabit today. The early Earth was bombarded intermittently until about 3.8 billion years ago, when the late heavy bombardment finally ended and the surface became more stable. Some of these impacts were large enough to vaporize the oceans and sterilize the surface, potentially setting back or eliminating early life and requiring it to re-emerge or recover from protected refugia. Whether life survived these catastrophes or emerged multiple times before finally taking permanent hold remains uncertain. The geological record from this early era too fragmentary to answer definitively. What we know is that by the end of the heavy bombardment, life was firmly established and would not be dislodged again. The Earth, at 4 billion years old, was a microbial world, its continents either absent or small and barren, its oceans teeming with single-celled life, invisible to any observer who might have watched from space. The atmosphere contained no oxygen, the chemistry maintained in a state that would persist for more than 1 billion years before biological processes finally began to change it. The sun was fainter than today, yet the greenhouse effect of the early atmosphere kept the surface warm enough for liquid water. This was the setting for the longest era in Earth's biological history, the age of microbes. The microbial age lasted from the origin of life around 4 billion years ago until the emergence of complex multicellular animals around 600 million years ago. A span of nearly 3.5 billion years when single-celled organisms were the only life on Earth. This era represents about 3/4 of Earth's biological history, far longer than all the time since animals appeared, yet it receives relatively little attention compared to the dramatic events of more recent periods. The microbial age was not static. Profound changes occurred during these billions of years, but its changes were often chemical and microscopic rather than the visible transformations of later epochs. For the first 1.5 billion years of life's existence, the atmosphere remained essentially oxygen-free. The chemistry maintained in a reduced state, where iron existed as soluble forms and the oceans probably had a greenish tinge from dissolved minerals. Life during this time was entirely anaerobic, using chemical processes that did not require oxygen, and in many cases could not tolerate its presence. These early metabolisms included chemosynthesis, using chemical energy from compounds like hydrogen sulfide, and various forms of photosynthesis that did not produce oxygen as a byproduct. The biosphere was productive but invisible, its effects limited to the chemistry of its immediate environment. Around 2.4 billion years ago, oxygen began accumulating in Earth's atmosphere for the first time. a transformation called the Great Oxidation Event that would prove to be one of the most significant changes in planetary history. This oxygen was produced by cyanobacteria, organisms that had evolved a new form of photosynthesis that used water as an electron source and released oxygen as a waste product. The innovation was revolutionary. Splitting water molecules requires more energy than earlier forms of photosynthesis could provide, and the oxygen released was a powerful reactive molecule that had never existed in significant amounts. The cyanobacteria did not know they were transforming the world. The oxygen released by cyanobacteria did not immediately accumulate in the atmosphere because it reacted with reduced compounds on the surface, particularly dissolved iron in the oceans that precipitated as iron oxide and settled to the ocean floor. These deposits formed the banded iron formations that are the primary source of iron ore today. Vast layers of iron oxide alternating with silica that record billions of years of oxygen production being consumed by chemical reactions. Only after the surface was largely oxidized did free oxygen begin accumulating in the atmosphere, eventually reaching levels that could sustain oxygen-breathing life. This transition took hundreds of millions of years to complete. The oxygenation of the atmosphere was catastrophic for much of the existing life. A mass extinction of anaerobic organisms that could not tolerate the presence of this reactive gas. Oxygen damages cellular machinery, disrupts metabolic processes, and was essentially a poison to the organisms that had evolved in its absence over the preceding 2 billion years. The survivors either retreated to oxygen-free environments, deep sediments, anoxic zones in the ocean, or evolved ways to tolerate and eventually exploit the new atmospheric chemistry. For those that could use it, oxygen offered a much more efficient metabolism, releasing far more energy from food than anaerobic processes could achieve. Around 2 billion years ago, a new type of cell appeared, the eukaryotic cell, characterized by a nucleus containing the genetic material and various membrane-bound organelles that compartmentalized different cellular functions. Eukaryotes are the type of cell that makes up all plants, animals, fungi, and many single-celled organisms, the fundamental building block for all complex life that would eventually evolve. Their origin involved a remarkable event, the engulfment of smaller cells that became permanent internal symbionts, providing new capabilities to the composite organism. Mitochondria, the powerhouses of eukaryotic cells, are the descendants of such engulfed bacteria, still carrying their own DNA and reproducing semi-independently within their host cells. The origin of mitochondria was crucial for the later evolution of complex life, because it provided cells with far more energy than they could generate on their own. Energy that could fuel larger cell sizes and more complex behaviors. Aerobic respiration, the process that mitochondria perform, extracts far more energy from food molecules than any anaerobic pathway, enabling the demanding metabolisms of animals and other active organisms. Without this energy boost, the evolution of complex multicellular life might have been impossible, the cells simply unable to generate enough power to coordinate and maintain large bodies. The engulfment that created mitochondria was a precondition for everything that followed. For another billion years after eukaryotes appeared, life remained predominantly single-celled. The famous boring billion, when relatively little, seemed to happen despite the presence of the cellular machinery needed for complexity. This period may have been constrained by low oxygen levels, which spiked during the Great Oxidation Event, but then declined and remained low for a prolonged period before rising again near the end of the Precambrian. Multicellular organisms did exist during this time: algae, primitive colonial organisms, but nothing approaching the complexity that would emerge in the Cambrian explosion. The biological machinery was ready, but the environmental conditions apparently were not. Around 600 million years ago, multicellular animals finally appeared in the fossil record. Soft-bodied creatures, leaving traces and impressions in seafloor sediments that provide our first glimpse of animal life. These ediacaran organisms, named after the Australian hills where they were first recognized, were strange and unlike any modern animals. Their biological relationships still debated among paleontologists. Some appear to be related to modern groups. Others may represent evolutionary experiments that left no descendants. The animal kingdom was beginning its long career, and within a few tens of millions of years, the diversity of animal body plans would explode into the variety we recognize today. The Cambrian explosion, around 540 million years ago, marks the moment when animal life suddenly proliferated into nearly all the major body plans that exist today. An evolutionary burst that occurred in a geologically brief span of perhaps 20 to 30 million years. Before the Cambrian, animal fossils are rare, soft-bodied, and often unrecognizable. After it, the fossil record teems with arthropods, mollusks, chordates, echinoderms, and other groups we can readily identify and classify. The sudden appearance of hard shells, exoskeletons, and mineralized structures made fossils far more abundant and durable. But the proliferation of body plans was real, not merely an artifact of preservation. Something had changed. The Cambrian seas were populated with creatures both familiar and alien. Trilobites crawling across the seafloor with their many segmented bodies and compound eyes. Anomalocaris, hunting through the water as the largest predator of its time. Small chordates with primitive notochords that would give rise to all vertebrates, including us. Eyes evolved during this period, providing predators and prey with new capabilities that sparked evolutionary arms races, driving rapid innovation. The ecological complexity of the Cambrian far exceeded anything that had come before, with food webs and ecological relationships approaching those of modern marine environments. The Cambrian was just the beginning of a long and eventful history of animal life. 500 million years of evolution that would produce everything from fish to dinosaurs to mammals to humans. Plants colonized land around 470 million years ago, transforming bare rock into the vegetated landscapes we take for granted today. Fish evolved, then crawled onto land as early tetrapods around 375 million years ago, beginning the vertebrate colonization of terrestrial environments. Forests rose and fell, continents drifted and collided, mass extinctions punctuated the record, and through it all, life diversified and complexified. The dinosaurs dominated terrestrial ecosystems for over 160 million years. From roughly 230 million years ago until the asteroid impact 66 million years ago that ended the Cretaceous period and their reign. This duration exceeds the time mammals have dominated by a factor of nearly 3, putting our current era in perspective against the long reign of these remarkable animals. The dinosaurs were not a failed experiment, but an extraordinary success. diversifying into thousands of species, ranging from sparrow-sized feathered creatures to the largest land animals that have ever existed. Birds are their surviving descendants, dinosaurs still flying among us today. The asteroid impact that ended the dinosaurs created a catastrophic winter that killed about 75% of all species, one of the 5 great mass extinctions in Earth's history, each of which reset the ecological relationships of the living world. In the aftermath, mammals diversified rapidly, filling ecological niches left vacant by the extinction, evolving from small, mostly nocturnal creatures into the diverse array of forms we see today. Whales returned to the oceans, bats took to the air, primates climbed into the trees, and the modern mammalian world took shape over the next 60 million years of evolution. Human ancestors diverged from other apes around 6 to 7 million years ago, beginning the long journey toward the species that would eventually wander about cosmic history and its place within it. The genus Homo appeared about 2 million years ago, with our species, Homo sapiens, appearing in Africa around 300,000 years ago. For most of our existence, we lived as hunter-gatherers, small groups moving across landscapes in pursuit of food, leaving minimal archaeological traces of our passage. Then, around 10,000 years ago, agriculture was invented and everything changed. The agricultural revolution led to permanent settlements, which led to cities, which led to writing, which led to recorded history, all within the last 5,000 years, an eye blink in the cosmic timeline we have been tracing tonight. The pyramids of Egypt, the philosophy of ancient Greece, the rise and fall of Rome, the medieval period, the Renaissance, the scientific revolution, the industrial revolution, the digital age. All of human recorded history fits within this tiny sliver of cosmic time. The universe existed for 13.8 billion years before humans invented writing and began recording their presence. The perspective gained from this journey through cosmic time is both humbling and elevating, revealing how recent our arrival is, while also showing how we emerged from the longest and grandest story ever told. We are made of atoms forged in stars, assembled on a planet that formed from cosmic debris, evolved through billions of years of biological history from single-celled ancestors who emerged from chemistry we still do not understand. Every discovery we make about the universe is a discovery about our own origins. Every glimpse of cosmic history, a look into the processes that produced us. The universe continues its evolution beyond this present moment, the story not ending with our arrival, but continuing into a future we can only partially imagine and predict. Stars will continue forming and dying. Galaxies will continue merging. The cosmic web will continue evolving for billions of years after humanity's brief presence has concluded one way or another. We are temporary observers of an eternal process, momentary consciousness in a cosmos that existed long before us and will exist long after. This perspective need not diminish us. We are the universe becoming aware of itself, atoms arranged to contemplate the atoms. The night sky you might see from a dark location contains stars whose light left them years or centuries or millennia ago. Each photon, a messenger from the past, arriving at your present moment, carrying information about where it has been. Some of those stars are young, formed after our sun. Others are ancient, born when the galaxy was young. The cosmic microwave background we detect with radio telescopes carries light from 380,000 years after the Big Bang. Photons that have been traveling longer than Earth has existed. Every direction we look into the past, and the story of those 13.8 billion years surrounds us completely, waiting to be understood. The universe is old beyond easy comprehension, and we are new, arriving in the most recent fraction of cosmic time to ask questions about everything that came before. Tonight, we have traveled through that entire history, from the first second when everything began, through the patient eons of preparation that led to stars, galaxies, planets, life, and finally, to this moment of awareness. The journey has been long, and sleep may have arrived somewhere along the way, but the cosmos will continue whether we are awake to observe it or resting peacefully beneath its ancient light. The story of 13.8 billion years has been told, and the universe continues its patient work, second by second, into whatever future awaits.